All right, discrete mathematics. We're going to start a new unit, a new chapter about algorithms. This is going to be chapter 3. And what I want to do to begin is just show you some examples of algorithms. Many of you who have already taken programming classes will have seen these sorts of algorithms before. These specific algorithms may be very familiar to you. We're going to do linear search, binary search, and bubble sort. But for those who don't have programming background, I recommend watching this just to kind of get a baseline understanding of the notation and what an algorithm is and what it does. So first of all, the algorithms we're going to be working with are written in something called pseudocode, which is not a real programming language, but it is very similar to a programming language. It's designed to be a way to communicate ideas that you could express with a programming language, but in a way which is just a little more natural and sort of easy to read. There is an appendix in the textbook, Appendix 3, which I recommend looking at if you are unfamiliar with pseudocode. It goes through kind of a pretty good explanation of what everything means. I'll try to explain it as I go as well, but you can look at Appendix 3 if you need more assistance with that. So what kind of algorithms are we going to be looking at? Well, an algorithm basically is just a procedure for solving a problem. And the type of algorithms we're going to be looking at right now are algorithms that work with a list. So if you're familiar with Python programming, a list is a type of data type. It's sort of like a particular type of object you can work with. It is an ordered thing, sort of like a string. So it's not like a set, because in a set it's unordered, and also a set shouldn't have any repetition, but a list is ordered, can have it. So it's the same as an array in C++. I don't know what they call it in other programming languages. So we're going to look at these algorithms that work on lists, and what they do are the first one is going to help us search for an element within the list, and then it's going to return, which is sort of like the output of a function. It's going to return a Boolean value, in other words, a truth value, true or false, and perhaps also. Oh, actually, sorry, my mistake. In this example, it's not going to return a yes or no. It's going to a Boolean value. It's actually going to return the location within the list of that like element that you're searching for. But if the element isn't in there, then it's going to return 0. Our lists are going to start with 1 instead of 0. I know that's going to be really annoying for programmers who are used to lists starting at 0. I'm sorry. In mathematics, we like to start things with 1 because that's the count. All right, so the second algorithm is going to be a search, another search. So we have linear search and binary search, just a different type of search with the same idea. It's going to return the location within the list of that item that you were looking for. And then the last one is going to be a sort algorithm. So it'll take a list and it will sort it in order. We're going to use numerical order. So let's begin with the first one. All right, so linear search. First of all, maybe read this. This is the type of thing we're defining. Procedure is like another word for a function in some way, or an algorithm. They're all sort of the same. The name of that procedure is follows right here. That's linear search. And then in parentheses are the inputs that we need to what's called pass to the function, pass into the function. These are the function inputs in the same mathematical sense of function inputs, right? So what follows is a list of the inputs with a description of what they are. So we say x is going to be an integer. So down here, you can see in my example, I'm going to run this procedure with 4 as being the input for where x is. And then we have a1, a2 up to an, which is a list of integers, n of length. So I have this list. I'm using square brackets to enclose my list. 1, 2, 3, 4. So those are my two inputs. Just have the number I'm searching for and the list I'm searching in. Then the procedure begins. Within the procedure, we can define variables. So here, the very first thing that happens is we define a variable I, which is going to be an index. You're familiar with indices from like studying sequences and maybe like Riemann sums, that sort of thing. We've done indices. It's a label. Usually we use positive integers. We're going to define an index I, and we're going to give it the starting value, assigned value of 1. That will change as we go. So the first step in my example here is going to be exactly that. We're going to say I colon equals 1. The colon equals is the assignment, assigned value to the variable. So now we have that, and now we enter a while loop, and a while is sort of like a conditional thing where as long as the condition specified by the while function is like true, then it's going to repeat some sort of sub procedure. So up here we see it says while I is less than or equal to n, and x is not equal to the ith element of the list, ai. While both of those are true, right? Because and requires both be true. We're going to continue to what's called increment the I variable. We're going to bump it up by 1. That means we're reassigning a value to I, which is equal to the previous value plus 1. So, so the idea here is we're searching through the list, and we're checking to make sure that we haven't gotten to the end of the list or beyond the end of the list. We're also checking to see if our ith element in the list is equal to the number we're searching for. As long as that's not true, we continue. As long as neither of those things have happened, we haven't gone beyond the list and we haven't found the thing we're searching for, we're going to continue bumping up the list, the increment. We're going to continue bumping up the index. So the first step here, we go into the while loop and we see that in fact, yes, 1 less than or equal to n. I should make a note over here that n is equal to 4, because there's 4 elements in my list. So 1 is less than or equal to 4. That's true. And 4 is not equal to 1. The first element in my list, A1. That is true. So what we're going to do is we're going to take I and redefine it to equal 1 plus 1, which is 2. So then we check again. Is 2 less than or equal to 4? And 4 not equal to the second element in my list? Well, the second element in my list is equal to 2. Is that true? Yes, that's true. So we bump it up again. I would then equal 3. And we continue to check. Is 3 less than or equal to 4? And it is the number 4 that we're searching for not equal to the third element in the list? The third element in the list is 3. So is that true? Yes, it is. So then we repeat the while loop. And then finally, is 4 less than or equal to 4? And is 4 not equal to the fourth element on the list, which is 4? Well, the first part of that conjunction is true, but the second part is false, right? This is false. That means now this is false. So then we stop the while loop and move on to the next thing. It says the next thing is an if then. So the question that it asks is if I is less than or equal to n. So I less than or equal to, sorry, I is now equal to 4. I should say that. I is 4 last time we assigned it. So is 4 less than or equal to 4? That's true. 4 is less than or equal to 4. So then we do what the then says to do. Okay, if the Boolean like question, the true or false question in the if operation here, if that is false, you don't do what the then part says to do, right? Because of like that's how implication works, right? You don't necessarily have, you can't guarantee the truth of the conclusion. But if the if part is true, then you do this. So we have to say location is defined as equal to I. So now, since we had true, we're going to do location will be defined as equal to the I value, and the I value is still set equal to 4 last time we did it, so let's do 4. Now, right here is a moment where we sort of create a new variable out of thin air. This is not good programming practice, but in pseudocode it's done all the time, so we're gonna be okay with it. We created our new variable there. Now the next line in the procedure says else. Now for those who are unfamiliar with an else statement, this means, well, if this part was false, so if I was not less than or equal to n, then you don't do this, but instead you do this, which would set the location equal to 0. So we're not going to do anything for the else. We're not going to perform this part at all. Skip it. Now the last thing is to return location. The last thing is to return 4. And that's the end of the function, the end of the procedure. So this was an algorithm, and the job of the algorithm was to find the element 4 in the list. It did, and it returns an integer that tells us the index for the number that it found. So in this case, because my list was just 1, 2, 3, 4, 4 was the 4th element. So it returns the number 4 because it's saying the number you're looking for is in the 4th position. All right, so the next algorithm I want to go over is binary search. And it is just another way to search through a list for a particular element and return the location. In this case, there's one important stipulation about the way you use the search algorithm, and that is the list of integers has to be in increasing order. It basically means it has to already be sorted. So if you have a list which is not sorted, it's all jumbled up in random order, you'd have to apply some sort of sort algorithm, like, for example, bubble sort or something else. In this case, I'm going to run the binary search algorithm searching for the number 7 in this list of prime numbers less than 10, 2, 3, 5, 7, 9. Since there's 5 elements in that list, 2, 3, 5, 7, 9, then n is 5. That's a piece of information that is not really like specified in the algorithm anywhere. If you were writing this in programming, like in a programming language, you might actually want to also specify as one of the inputs to the function the value of n, the length of the list. Or you might want to employ a function on the inside of your algorithm that counts the number of elements in the list before going on. Anyway, just wanted to point that out. So what does this algorithm do? First of all, it introduces not one index, but 2 indices. So we're going to say I is defined to equal 1, and then we're going to say j is defined to equal n, 5 in this case. So I'm going to write this on the same line just to save some space for right now. All right, so why are we defining 2 indices? The reason we're defining 2 indices is because what we're going to be doing is we're going to have sort of a search interval within our list, which is the 2 index values. And the idea is, with a binary search, start with those search interval being the entire list, and then we're going to find the midpoint, the rough midpoint, because we have to round it to the nearest index. We find the midpoint and check to see if the number we're looking for is a greater or less than that midpoint value. That's why the search list has to be in increasing order, because you need to be able to rely on like checking inequalities to see if the number you're looking for is in the first half of the list or the second half of the list. So I'm going to draw a little picture of this up here. Imagine you start with the search interval being the entire list. You find the midpoint, and then you ask, is X, the thing you're looking for, is it on the left side or the right side? Let's say you check and you find X. X should be somewhere on the left side. Well, what you do then is you redefine your search interval to be just the left hand. And you say, all right, here's my search interval. Find the midpoint, and then ask, is X on the left or the right side of that? Well, let's say X is on the right side of that. Then you redefine your search interval to be just this. You find the midpoint, and you repeat. Which side is X on? Let's say it's on the right side. Well, then this is your search interval. You find the midpoint. Where is X? Say it's on the left, then eventually you'll find X, right? Because eventually the left and the right sides of your search interval, which are going to be the index variables I and J, eventually they will meet and they'll like equal each other. And then, or maybe the midpoint will equal one of them. And then that number is X, right? So this approach is a quicker way to search through a list. Let's see how it works. So we've got I or J. In our example, I is 5, J, sorry, I is 1, J is 5. Then we enter a while loop. Is 1 less than 5? Yes. So in the while loop, we're going to introduce a new variable called m for midpoint. In this case, m is going to be set equal to the floor function. This is called the floor, which basically means round down to the nearest number. And so then we're going to do 1 plus 5, because those are the values of I and j over here. And then divide that by 2. So this is equal to 6 divided by 2 is 3. Rounded down is still 3. So we've set the m index equal to 3. So now we're going to check an if function. Is x greater than am? So x is 7, right? This is our x value here. It's 7. Let me put that in red since it's a comment. There we go. And so now we check, is 7 going to be is 7 actually greater than the mth element of the list? So am in our case is this one. I'll put a little label on that as well. A is the name of the list, and it's A3, right? So the question is 7 greater than 5? That's true, yes. So what we do is we do what it says to do in the then part. We're going to execute the then statement, not the else statement, right? So it says then I will take the index I and reset that equal to m plus 1. M was 3, so now we're going to reset it to equal 4, right? So the next thing we'll do is get to this basically takes us to the end of the while loop. And now we're going to go back and do the while loop again, because we got to keep going through the while loop until this is false, right? So I equals 4, j equals 5. So we check. The while question is I less than j? Is 4 less than 5? Yes, that's still true. So we'll perform the while loop again. So we'll say m colon equals, and now we have to perform this calculation again, but with I equals 4 and j equals 5. So we go floor of 4 plus 5 over 2. Now that gives us 9 divided by 2 is 4.5, rounded down equals 4. So now our m value is 4. So now we move on to this if statement. It says if x is greater than am. So let's see, what are we going to do? X is 7. And we ask, what is A4? Because m equals 4. A4 is this one, the 4th number in our list. So we ask, is 7 greater than 7? No, 7 is not greater than 7. That's false, right? So what we're going to do is, instead of applying the then statement, we're going to apply the else statement, right? Because it says if x is greater than am, then do this, else do that. And so we're going to do the other thing. To do the j will be set equal to m value. So j will be set equal to m, which is 4. So now at this point, I is 4 and j is also equal to 4, right? So now when we return to the top of the while loop, we check this inequality. Is 4 less than 4? No, it's not. So we're not going to run through the while loop again. So now we move on, right? So we move past we're finished with the while loop. We move past the while loop and check the next. We go to the next line in the procedure. If x is equal to ai, well, ai is the a4, which is equal to 7. So we're going to ask, is 7 equal to 7? Yes, it is, right? That's true. 7 equals 7 is a true statement. So I guess I should put it like that. 7 equals 7 And actually, in coding, you would do like a double equals. So checking to see if 7 actually, here, let me make that a little clearer. In most programming languages, you use double equals to check to see if it is like, if the values are the same. Like it returns, the double equals basically says, like it returns a Boolean value, true if these two things are equal, false if they're not equal. So that's kind of, we don't necessarily need to use double equals in pseudocode, but that's for you programmers out there. That's what that is. So that's true. 7 does equal 7. So we are going to perform the then, which is location set equal to I. We'll do our location signs the value of I, and I is currently equal to 4. Right, that was the last thing we set I equal. So location is 4. We don't perform the else thing because we did find the element we were looking for, and then we return 4. So that was our that was an example of performing that binary search, right? We didn't have to cut in half very much. I think we just sort of cut in half and then half again, and we found it. It's pretty quick, but that's how that works. Pretty good. We'll study later. We'll compare the linear search and the binary search, and we can talk about which of them is going to be a more efficient way of doing it, and how fast are these search algorithms. All right, so the last algorithm I want to show you it's a type of sort algorithm. This is one of the simplest, least efficient types of sort algorithms, called bubble sort. Called bubble sort because it kind of resembles like bubbles floating from the bottom of a straw up to the top of the straw. Everything kind of bubbles up to the top, and things and elements in the list get moved to the top of the list when they're like big. The big things move to the top, and the small things get kind of pushed down. So that's why it's called bubble sort. So the way it works is to have two nested loops. So this uses a for loop instead of a while loop. It means that we're just going to have an index which bumps up one by one within a range of values. So in our case here, we have this list 4, 2, 3, 1. So n equals 4 again, and we have it says for I from 1 up to n minus 1. So we're going to bump up I. It's going to be I equals 1, then I equals 2, and then I equals 3. And we're going to stop at 3 because that's 4 minus 1. So each time we run through the loop, we're going to also define this new variable, this other index variable j, which has its own for loop running inside there. So inside of the first loop, when I equals 1, we're going to have j. And j is assigned the value starting with 1 and going up to n minus I, which means when we start, j is going to go from 1 to 3. But then when I equals 2, j will just go from 1 to 2, because 4 minus 2 is just 2. And then when I equals 3, j will start at 1, and then it'll end, because it won't go to 2. It'll just do j equals 1. So that's the idea. So like the j is getting shorter and shorter. The sort of, I guess from your perspective, it would be this side, right? If this is like 1 and this is 3, the j range is getting smaller from the top. Anyway, you'll see how it works. So we have I equals 1, and then we assign j equals 1, and now we ask a question by an if statement. Aj is greater than aj plus 1. So if j is 1, we're gonna compare a 1 and a 2. Whose values are 4 and 2. So we ask, is 4 greater than 2? Yes, it is. Certainly is. So we do something. What we're going to do is interchange AJ and AJ. So in this case, we're going to take the 4 and the 2 and we're going to interchange them. So my list is now going to be reset equal to, I'm going to call it list. I know I never defined that, but this is just pseudocode. My list is going to be reset equal to 2, 4, 3, 1. So there I have interchanged these two elements, 4 and 2. They've been swapped around. So now j is going to bump up to the next value. J will equal 2. And we're going to check with our new version of this list, we're going to check A2 and A3. So now A2 is 4 and A3 is 3. And we ask the question, is 4 greater than 3? Why, yes, it is. So we do the same thing again, except with elements 2 and 3. So we're going to have 3, 4. You can see now these two have been swapped around. And we have one more value of j for this time through. So we bump up to j equals 3. Now we're going to compare A3, which is now 4, and A4, which is still 1, and ask the question, is 4 greater than 1? Why, yes, it is. So we do one more round of this bump of this interchanging with 2, 3, and then we'll have 1, 4, like so. And you can see those have been swapped. So you see, every time you redefine what the list is, then the name, then the values of A, like the value of A2 is originally 2, but after this interchange, this first interchange, the value of A2 is now 4. Now there's a second interchange. A3 gets swapped from being 3 to being 4. So you have to keep track of what the list is at any given time. So this is the end of the J loop. So this J loop is now complete. We've gone from 1 to 3, which is the n minus I value. So we're gonna go back to our outer loop, and we're gonna increment the value of I from 1 up to 2. So now we start the J loop over again. J starts over at 1, but it's only gonna go up to 2 this time. It's not gonna go to 3. And the reason for that is because the element, which is the biggest element in the list, has already been moved to the far end of the list, right-hand end of the list. So we don't need to bother looking at that rightmost element of the list any longer, because we already know that's the biggest element in the list. That's what has happened now after the first time through the J cycle, through the J list, or the J loop, I guess. Okay, so I is 2, J is 1, and so we go back to the beginning of our list and we check. Is A1 and A2, are they is 2 greater than 3? No, it's not. That's false, right? So no change. The list is going to stay exactly as it is. No change. And then we increment J to 2, and we ask, is the second element, A2, greater than the third element, A3? So is 3 greater than 1? It sure is, yes. So we're going to do another interchange. List will be redefined as 2, 1, 3, 4, like so. Now that you see, we've swapped those two, and that's the end of that J loop. So we go back and we increment I one more time to 3. This is the last I we're going to do, because I only goes up to n minus 1, which is 3. With n being 4, right? So this is the last time through the I loop, and this time the J loop only gets only has one step loop. J begins at 1, and that's it. So we're going to ask, is the first element, A1, is it bigger than the second element, A2? Is 2 bigger than 1? Yes, it is. So we're going to do one last interchange. List is set equal to 1, 2, 3, 4. And that is the end of the algorithm, end of the procedure. Now, this procedure, the way it's written, it doesn't return anything, doesn't have any value that it like sends sends back as a return. If you were in programming language, this would be like as a function is like a null data type function, returns null. But what happened via this procedure is that the original input list got edited. So at the end of the procedure, it might not return anything, but the list that it was working with is a different list, right? This list is no longer 4, 2, 3, 1. It is now 1, 2, 3, 4. So that's how bubble sort works. And I think that's the end of our examples.